Good afternoon to you all. I want to welcome you, all participants and all presenters to this Carbon Capture Technologies webinar, in which we put specific focus on the potential of clathrates for CO2 capture. In this webinar, we will share some of the results from the research being performed in the Carbon2Value project, the EU project, which was co-financed under the EU Interact 2Cs program. We are very happy that you're all here, and we are very happy that we have been successful in putting together an interesting and very concise program, and with excellent speakers, which I would say are all experts in the field they operate in. My name is Geoffrey Schouten. I will act as your host today for this webinar. And I think, as we are now all used to after 1 year of COVID pandemic, working online, and there are certain rules we'd like to ask you to adhere to make sure that we have a smooth running webinar. First and foremost, please turn off your microphone unless you're one of the speakers, of course, or unless you have a question for which I ask you to put it into this webinar. And it also works, by experience, we know it works better if all the participants, except for the speaker who is at that moment presenting, everybody to turn off their cameras. That will definitely increase the performance, or will guarantee optimal performance in this webinar. Questions can be put in the chat function, as you will see in the bar below with all the icons. If you have any question, either technical or a content question, please put them in the chat, and we will monitor that continuously. And relevant questions, we will try to answer as many questions, and we will either answer them in this webinar, or otherwise we will collect them and get back to it later. This webinar is being recorded, as you might have seen, so we'd like to put your attention to that. This is to allow participants to view the webinar afterwards again, or people who are not in the possibility to take part in this webinar, that they can view it afterwards again. At the 22nd of June, and a little bit more, or in 2 weeks from now, we will also host another Carbon2Value event. That's our end event. I would very much like to invite you to participate in that event as well, where we will share more information, and we have also constructed an interactive program, and you can register through the Carbon2Value website, which we will put on the screen later on. We will a little bit later, we will ask you 3 questions by poll. Here you see the website where you can go to. Again, we will ask those questions in 5 to 10 minutes from now, but at least you can go to the website already, pollev.com, ISPT warmte, WARMTE 673, or scan the QR code. And again, we will put them on the screen a little bit later, but you can already log in there. And my last remark would be that this presentation, all the presentations that are being given, will be sent to you after this webinar. We will send that information together with the recording, or a link to the recording, and answers to the questions that are posed. And we will send that to the email which you use to register yourself with. Then I would like to introduce to you Matthijs Ruitenbeek, Senior Scientist, Carbon Management and Circular Economy at Dow Benelux, and he will briefly introduce to you the Carbon2Value project and outline the program that we put together for you. Matthijs, would you be so kind to share your slides?
Yeah, thank you for the introduction, Geoffrey, and welcome everybody. I will not contribute to the technical content of this webinar, but I will slightly take some time to introduce the consortium, so you know from where this seminar comes. We are a consortium consisting of several parties active in the Interreg 2Cs area, so in Belgium, in the UK, in France, and in the Netherlands. We have industrial parties and also research institutes as well as academia in the consortium, where we spent in total about 7.5 million budget with co-funding from the Interreg 2Cs program. And of course, we have our own website, so you can look at all the details later. In the consortium, we had the task to develop low carbon technologies, doing something with CO2, but especially also with carbon monoxide. And we have focused on the steel industry. So ArcelorMittal is our lead partner, providing the gas for the downstream units. And in this schematic diagram, you see that we have a number of activities in the program, including a classical amine sorption unit for CO2. But in the program, we have looked beyond, and we looked today especially at the clathrate work that has been done by the University of Lille, where they looked at an alternative for the commercial solution that we have applied in the program. Ultimately, of course, the goal would be to utilize the carbon monoxide that is free of CO2 in downstream operations, including the LanzaTech technology for syngas fermentation and Dow technology for syngas conversion, but also the CO2 could be utilized or stored. What can you expect from today? Well, we have 3 speakers from associated partners and consortium members. First, you get a state-of-the-art review by Jurian Boon from TNO, followed by a presentation of the work that has been done in Lille on the development of clathrates for CO2 capture. And ultimately, of course, we asked ourselves the question, how would a process for CO2 capture with clathrates look like? Where are the challenges and what are the potential costs for that? And with that, we had a team from the University of Twente working on conceptual process design aspects of this technology. And hopefully by the end of this seminar, you will have a clear view on what is possible with this option and whether it would be competitive to the state-of-the-art that has been presented as well, and the commercial or more commercial type of applications that we will present on the 22nd of June. And with that, I think we should go back to Geoffrey, who will probably touch the poll again before we move into the technical content of today's webinar.
Great, thank you, Matthijs, for this brief but yet very complete introduction. Yes, indeed, we would very much like to ask you 3 questions. I hope everybody had the opportunity to surf to the link we gave you, pollev.com. ISPT warmte in Dutch heat 673. And if you go there, and I hope everybody has that link now, maybe we can also put it in the chat to be sure that everybody got it. And then I would like to ask to have the first question on screen. We are very interested where all the participants in this webinar are based. Where do you live or work, or where are you currently? Would you be so kind to answer that question? We were hoping for an international crowd. As we are running an EU project, it's also to be expected. Latvia even, wow. We're talking France, the Netherlands, still waiting and hoping for the UK, Sweden, India. Okay, I allow for 10 more seconds before we move to the second question. All right, thank you very much. The second question, would you be so kind to inform us on which sector you represent today? And if none of them match, please use the one that comes closest. So we have the hard to abate industries, steel, chemical, cement, of which 2 are represented quite a bit. The energy sector also, well, maybe not surprisingly, or it is, but large attendance from that sector. No R&D centers yet, which surprises me a bit, to be very honest, but it might come still, or they see themselves as part of scientific community. The first one. Okay, I'm just waiting to see if the numbers stabilize a bit or if they keep changing. So again, I would say I allow for 10, 15 seconds more for everybody to have the time to complete this question. All right, scientific community taking the lead, followed by energy sector, and steel and industry still battling who comes first. Okay, let's go to the last question, please. Why were you interested in this webinar and in carbon capture technologies in general? And once again, please choose the answer which comes closest. And in the meantime, because some people might have joined later, we would kindly like to request from you to turn the microphone, both the microphone and the camera off, to guarantee optimal performance in this webinar. Thank you. All right, allowing for, again, 10 more seconds, see if we have anybody who is into policy making. Or to take the lead over engineering design opportunities. Ooh, it's a draw now, not anymore. All right, last 5 seconds. All right, thank you very much for being so kind to share that with us. Then I would very much like to now move to the content, all the interesting content for which you came, I would say. I would very much like to introduce to you Jurjan Boon, Senior Scientist Process Technology at the Dutch Research Institute TNO. He will provide us with some context and tell us about status and outlook of current CO2 capture technology. Jurjan, if you would be so kind.
Thank you, Jeffrey. I hope you can all hear me right. Then I will present. It's by no means meant as an exhaustive overview of everything that's going on, but I would like at least to leave with you a flavor of some of the things that are currently ongoing, I think, in Europe and throughout the world in terms of CO2 capture and how the recent trend towards more efficient capture can really pave the way for the implementation of CCUS as an industrial technology. Well, let's briefly recap why we're all doing this. There it is. Yeah, sorry. Well, I think we're all aware of the call to action, let's say, from the European Union, aiming to be climate neutral by 2050. That means an economy with net zero greenhouse gas emissions. An urgent challenge, and at the same time also an opportunity to develop new technology and build better and more efficient processes. And the EU is ready to lead by investing in what they call realistic technological solutions. So technology plays an important part in achieving these greenhouse gas emissions. And if you look at the figure on the right, you can see that greenhouse emission intensity has gone down severely. At the same time, the targets for 2030 and even 2050 are still quite a long way. So indeed, new technological solutions we called for. Well, looking at the industry, you see industry as one of the many different sectors on the left. And again, it is shown that industry has reduced its CO2 intensity already significantly, mainly due to energy efficiency measures. At the same time, much more steps are required in the near future. Now, if we make a subdivision of industry in terms of different sectors again, then it's clear that the iron and steel industry, as well as the cement industry, actually play an essential role in terms of CO2 emissions and CO2 emission reduction. Now, reducing the CO2 emissions is hard in itself, but at the same time we see the demand in industrial products on quite a steep rise, which is linked with the growth in GDP. So actually this is good news. At the same time, this makes the challenge of reducing CO2 emissions even more stronger. So we see a big rise in the demand for plastics, and also steel. The steel demand has risen and will continue to rise. The two sectors that are at stake today. Well, look at the most important industries. I think it's important to realize that the different options that are there. If we look, for example, at the steel industry, this is a report by the IPCC, the International Panel on Climate Change, and they have identified different technological solutions to reduce the CO2 footprint. So they range from decarbonization of the electricity supply, advanced blast furnaces, natural gas, DRI, different iron making technology, and scrap-based electric arc furnaces. And each of them can deliver a significant reduction in CO2 emissions from the current global average of CO2 intensity. At the same time, it is also clear that neither of these initiatives will be able to reach really deep decarbonization, except maybe scrap-based electric arc furnaces, but that will not be able to make up the supply of new iron. So this is basically recycling.
Sorry, we've lost the slides.
Oh. That's weird. Let me see what I can do. Going to disconnect.
Yeah, that's the same here as well, Jurian. Maybe you can stop sharing and try again, because I hear you perfectly here. But
okay.
Indeed,
we can hear you perfectly. It's just the slides have been lost.
and we also, now that I have the opportunity, we are also, it seems like, at least for me, myself, the chat is not available. We are working to solve that issue. Oh, I see somebody else tried to share the screen. Maybe that was the reason for it. Okay. If we are working on the issue with the chat, please continue, Jurian.
Are the slides visible again?
Yes, they are.
Okay, that's good. Well, let me quickly continue. And well, in terms of industry transformed, the old adage is to reduce, reuse, and recycle. And we see that a new, well, let's say a new way of thinking in terms of industrial symbiosis is arising. And if you look at these figures from the International Energy Agency, you see the different options to reduce CO2 emissions. where CCUS plays an essential role for the cement, iron and steel and chemicals industries, the orange pie sections. There's also an opportunity for fuel and feedstock switching, which is actually the topic of the Carbon to Value project. So to integrate the steel mill with the plastics industry, as Matthijs has explained in the beginning. Well, some final remarks about CCUS. CO2 capture is essential in the energy transition. It can be retrofitted to avoid significant amounts of CO2 from existing infrastructure. It can tackle emissions in difficult to decarbonize industries, cement and iron and steel, chemicals possibly that have been discussed. And it can also set up the infrastructure to be able to move towards synthetic fuels and feedstock for long distance transport that are still required by 2050 and well beyond. It enables a quick ramp up of the low carbon hydrogen economy by producing blue hydrogen. And it can be carbon dioxide removal technology to remove CO2 from the atmosphere. And that's what you see in the IPCC figures on the bottom right, where for different scenarios, the role of bioenergy with CCS to remove CO2 from the atmosphere varies in different degrees, but for most of the scenarios is an essential element. And on the bottom left, you see the current initiatives that are there, either commercial CCS, mainly enhanced oil recovery, also pilot demonstration and CCS hubs for CO2 emission reduction. Now, let's look a bit more at the what. What do we need to do if we want to capture industrial CO2? Now, industry is concerned with the making of products from feedstock, and currently that's fossil feedstock. And during the energy transition, we will no doubt move towards more bio-based feedstock. But in the end, for the chemist, that changes some things. But the carbon and hydrogen will still be the main constituents. And we have an industry that creates these products from the feedstock. Now, of course, we have air to combust the feedstock and generate the heat that's often required to produce these products. That means that out of the stack, we have a mixture of CO2, steam, and nitrogen coming out. So this is, let's say, a very rough simplification of the chemical industry. Yeah, I'm a chemical engineer, so I'm very fond of simplifying things. And if we follow the trajectory of the CO2, where it came from and where it ends up, we can draw along this line a figure of the concentration of CO2, really. Because from somewhere along this line, we need to capture the CO2. And the reason I'm looking along this trajectory is because there is a big difference in terms of the concentration of CO2. As I've tried to indicate here on the left, all the way at the end, when the CO2 is mixed in the air, we end up with about 400 ppms of CO2 at 1 bar. So that's a very low concentration of CO2, very dilute. You could also think of end-of-pipe solutions that are in the tail gas of the process, let's say, and capture the CO2 there. Then typically you are at 100 millibars of CO2. At the same time, it's also possible to capture the CO2 before, even in the process. That's what we call in-process CO2 capture. And the figure here on the left shows the importance of doing it as early as possible, the CO2 capture, because with the increase of the CO2 partial pressure, the the ideal work that is required for the separation of CO2 is strongly decreased. So by moving earlier in the process, we significantly reduce the work required for the CO2 separation. Now, this is the ideal work, and the situation becomes even more severe if we also look at the efficiency of the process, because also the efficiency tends to increase with increase in concentration, or a reduce in concentration factor, as is shown in this graph. And then finally, in terms of the economy of the process, again, with decreasing concentration, we see the price of many separation processes shown in this graph follow this trajectory, where you have a significant increase in the price of a separation process, the more dilute the species is you want to capture. So all of these three effects combined point quite strongly in the direction of what we call in-process CO2 capture. So to summarize, that's also where the innovation potential is. So the efficiency and economy are drivers for in-process CO2 capture on concentrated streams, and the market for CO2 capture is really significant. And a recent publication from colleagues of mine at TNO in Amsterdam has shown that 30% capex reduction saves $17 billion per year by 2050. So there's really a strong driver for the improvement of the efficiency and capex of CO2 capture. Now let's look at what can be done for steel gases. This is a simplified scheme of a steel production process, where we have coke production, a blast furnace to produce iron, and a basic oxygen furnace to finally produce steel. And there are three main sources of CO2 from these processes: the blast furnace gas, the basic oxygen furnace gas, and the coke oven gas. And currently, the energy content of these streams is utilized internally for about 50%, which creates 50% of the CO2 emissions. But there's a lot of energy left, which is generally combusted in a power plant, which creates the other 50% of CO2 emissions, roughly. Now, different ways to capture the CO2 from these gas streams are absorption, which is a gas liquid process. You contact the CO2 containing stream with a liquid that is able to absorb the CO2, which can then be released upon heating of depressurization. Now, different technologies out there vary from chemical absorption to physical absorption, where a physical solvent typically produces a more linear graph of the absorption capacity versus partial pressure, which means that at the higher partial pressures, physical solvents are favored, whereas CO2 capture from more dilute streams, lower partial pressures, chemical solvents are typically preferred. And then there's Rectisol and Seluxol commercial processes available to capture CO2. First one with chilled methanol, and second one with DEPG. Now, next to absorption, cryogenic separation is an option. Now, this comes with a complexity that it cannot be used for too dilute streams. And well, too dilute is actually an understatement. You need typically above 90% CO2 in your gas stream to be able to use cryogenic separation efficiently. And then still, the energy penalty is an issue because of the regeneration and steam removal that is required. Still, these systems are proposed for further purification of already concentrated CO2 streams to make them sequestration ready. Then in terms of adsorption, actually the topic of today, different technologies have been proposed, ranging from pressure swing adsorption, vacuum swing adsorption, and temperature adsorption. And these systems have in common that they are multi-bed processes. So you have one or more beds that are adsorbing CO2, while other beds are being regenerated, so that the ensemble of the different beds create a continuous cycle that recovers the CO2 from a stream. Now, in these adsorption-based systems, it's always important to look at the trade-off that you can reach between the CO2 recovery and the CO2 purity. So the more CO2 you recover, the more difficult it is to reach a high CO2 purity. And then finally, membranes. Membranes are still, membranes for CO2 removal are available, but for to make them economical, more research is being done, and different membrane types have been proposed. Two major classes are CO2 selective membranes, as you see here on the top right. There's a membrane system that selectively separates CO2 from a gas mixture, and at the same time, hydrogen selective membranes have been produced, as you see on the bottom here, which are able to selectively remove hydrogen from a gas mixture. And in the latter case, it's important to convert all your energy, so all the CO and hydrogen, into hydrogen, which can then be removed, which means that you separate actually the carbon from the energy content of your gas stream. Now, in looking again at the steel production case, clearly these three gas streams can be treated with the techniques I've just mentioned. I think it's important in this stage to also recall new developments in steelmaking, or in iron making, I should say, which is top gas recycling, which is basically an oxy-fuel technology. You remove the nitrogen from the air that's normally used in the blast furnace, which means that you end up with a concentrated stream of CO2. Actually, you still need a CO2 separation unit, but the CO2 separation unit has to deal with a lot less nitrogen, so it's much more easy to perform this separation. And at the same time, it allows you to recycle a concentrated carbon monoxide hydrogen stream into the blast furnace. Well, like I said, top gas recycling is a very big improvement in iron making being considered. At the same time, it still needs a CO2 separation unit. So all of the above is still valid, also in case of top gas recycling. And in terms of different technologies that are currently being piloted in the iron and steel industry, it's good to have a look at the list in the reference here at the bottom. It's quite a good reference, really recommend it. And different options are, of course, hydrogen DRI. The DRI is an option we've discussed before. But other options contain vacuum swing adsorption. MEA is a liquid system, and DEA is a liquid system. And then in terms of other iron making technologies, it's good to realize that many of them still rely on CCS, or actually nearly all of them.
Julian,
yeah.
Can I please ask you to end your presentation in 5 minutes?
Yeah.
Would that work for you?
should be fine. Yeah, let me speed up a little then. Well, for your reference, if you're interested, have a look. This is also copied from the same reference, some recent initiatives. Now, as I've already said at the outset, it's impossible for me in 25 minutes to present a complete overview of everything that's being done in terms of CCS, even in the steel industry alone. So my proposal is to focus a bit on the adsorption, which is really the topic of today. Adsorption for CO2 separation is a technology that is not novel in itself. So commercially existing zeolites and active carbons are available to do a pressure swing adsorption for CO2 removal. At the same time, these processes are really energy intensive and sometimes also capex intensive. So new developments are on the way to improve the efficiency of CO2 capture. And three important routes, I think it's good to mention: high temperature materials, calcium-based predominantly, intermediate temperature-based hydrotalcite, and low temperature adsorbents. Well, to give you again a flavor of some of the developments. For calcium, the Spanish Research Council, CSIC, is proposing a what they call CASO process, where they do a calcium looping. Calcium oxide is actually the species involved in binding with the CO2 and then releasing it again upon regeneration. At the same time, working with a copper-based oxygen carrier in this process. And as you can see here on the right, the different steps in steelmaking can be treated with different manifestations of the CASO process. And currently, the CASO process is a prototype is being constructed at TRL7. The hydrotalcite-based route is also being developed at TRL7 currently in the Initiate project, where already in a predecessor, the stepwise project, it was shown that the different streams of the steel gas can be treated separately or together, which then in the end leaves the highest CO2 reduction potential. Can go down to 0.6 tons of CO2 per ton of steel at a CO2 avoidance cost of 33 euros per ton. With the current ETS price of 53 euros per ton, that's not bad at all. So promising development. And then, Jeffrey, I'm glad I can end my presentation here because I think another important topic of today is the clathrate hydrate, a new development in low temperature adsorption process. But I'm definitely not the best placed to tell you anything about that, so I will leave that to the other presenters. Thank you for your attention.
Thank you very much, Julian, for your presentation and overview. And although, as you said yourself, time is way too short to come anywhere near a complete overview, I think you did a fantastic job. So thank you very much for that. I think we are still facing issues with the chat, although we are now experienced for more than a year. We run into this issue, and we apologize for that sincerely. What I forgot to address specifically, again, is that there is room for questions. We have 5 minutes for questions, and since the chat doesn't work, I would propose that people raise their hand, use the icon to raise their hands if somebody has a question for Julian. And I see no hands so far. So either that functionality is savior of today. Michiel Mackay, and maybe I can ask you to turn on your camera and a microphone and ask your question to Julian directly.
Yes, thank you, Joran. Long time ago, we spoke to each other.
Nice to see you.
I have a question on, I think, the first slide where you show the CO2 emissions. What took me by surprise is the CO2 from biomass is increasing like hell.
Sorry, could you repeat your question?
I'm still in?
Yes. The last part of your question I missed, sorry.
In one of the first slides, you see all the CO2 reductions, and there's one line, the CO2 from biomass is increasing like hell.
That's this one. Yeah, excellent question.
And what is that the cause of that? That we come to sustainable biomass, but that increases like CO2 like hell. But all the reduction is increasing by biomass.
I don't know the origin of this. No, sorry. Good question.
Can you look up for that? Because this is a really bad sign, in my opinion.
Yeah.
I think Jurian, we will dive into it, find the source for that, and get back to you and answer that question.
Yeah.
Good question.
Thank you
very much. Is there anybody else with a burning question? Jurian, I think people are either shy or your presentation was very clear.
Wow.
I see Ludwin Dahl. Can you please turn on your camera and microphone and pose your question?
Yes, good afternoon. Thank you for the opportunity to ask a question. I saw on one of your slides that you mentioned that several billion euros are going to be saved if we save on capex by 20 to 30%. What is the effect of reducing the OPEX cost on the savings to 2050? Can you say something about that?
Yeah, let me check. Yeah. Yes, well, the capex will be significant. Sorry, the OPEX reduction will be a significant impact as well. To quantify it in a similar number, I'm not sure if I can provide you that. But in the end, we in process in CO2 capture, the important parameter is to look at what has been called the SPECA by Politecnico di Milano, who've done a lot of system evaluations of different capture options, which is the SPECA is the specific primary energy consumption per CO2 avoided. So it's important to look at your reference case, basically industry as it is now, and your new proposed process, and look at the difference in the in total cost, both capex and opex, and the difference in CO2 emissions. And the ratio of those two numbers will tell you the specific, will tell you the SPECA. And in the end, I think that's the essential parameter that we should strive to minimize.
But is that like a ratio between the two, the capex and the opex, or you can't say that really depends on the industry?
Yeah, in the end, it's the ratio about the investment that you have to do and the OPEX, so that's one aspect, and the other aspect is the delta in CO2 emissions.
Thank you.
Okay, thank you very much for your question, and Jurian, thanks again for your presentation and answering the questions. Unfortunately, we have strict and tight programs, so I would like to go to the third session. And for that, I would like to introduce to you Bertrand Chazalon. He's a professor at the University of Lille in France. And Jurian, as you already hinted to, he will introduce us into the world of clathrate hydrates as a promising new system for CO2 capture. I want to inform you what you will see now is a pre-recorded version of his presentation. So that's what we will play now. Afterwards, Bertrand will be available live in this webinar to answer any question you have. Okay, now you would say let's start the presentation, please.
Good afternoon, everybody. So I'm Bertrand Chastalon. I'm a professor at University of Lille, and today we'll talk about the clathrate hydrates as a promising new system for CO2 capture. This work has been undertaken within the context of a carbon-to-value project of Interact2C program. So the context, there exists a range of solutions that can be implemented to limit and control CO2 emissions from large-scale industrial point sources, which are related to energy consumption. So CCS, carbon capture and storage, prevents CO2 from being released into the atmosphere by capturing CO2 produced by industrial plants. As we have seen in a previous presentation, this is a proven and well understood technique. And for example, CO2 emission can be reduced by 80 to 90% for modern power plant equipped with CCS technology. On this world map here, we can see the growing presence of CCS around the world. And in 2019, the number of large-scale CCS facilities has increased to 51, while there are about 40 pilot and demonstration scale CCS facilities operating or about to be commissioned. All these constructions have the capacity to capture and permanently store around 40 million tons of CO2 every year. And this number is expected to increase by about 1 million in the next 18 months. So we can see here the current CCS method under investigation. So I will not enter into the details of all these techniques, but we can see that they all show advantages and also drawbacks. So the most commercially mature are both of the chemical absorption and physical absorption techniques, and but they still present some inconvenience. So with this consideration, it appears that there is a need to develop innovative CCS techniques that are economically and environmentally viable for large-scale application in the short to medium term. And the next generation technologies are needs to be developed to drive down CCS development cost and shorten the deployment timelines. And so the next generation capture technology will have innovative materials or process or equipment which will reduce the capital and operating costs, but also will improve, needs to improve the capture performance. In this context, one of the alternatives is the Hydra-Based separation process, which can be applied in to the different CCS technology. For example, in the post-combustion here on the left, the fuel, which is generally fossil fuel, and the oxidants are used to produce power, and the exhaust flue gas is sent to a capture unit, which is where the HPSP can be applied to separate CO2 from the other components. Generally, the other components are nitrogen or carbon monoxide. And so the CO2 hydrates which has been produced can further be transported for long-term storage. So this HPSP process can also be applied to industrial or pre-combustion CCS technology, where the gas to be treated varies significantly. In pre-combustion, for example, the CO2 needs to be separated from hydrogen. So what and why using this hydrate process? So what are hydrates or gas hydrates? Gas hydrates are actually crystalline inclusion compounds that encapsulate gas molecules. They occur naturally on Earth and represent a huge natural gas energy reserve, which is higher than oil and coal, and they contain hydrocarbon gases like methane or ethane. We can see here in this picture a natural occurrence of gas hydrates. They generally form along the continental margin or also in the permafrost region. So how do these clathrate hydrates form? So they form a different structure, as we can see here on the right, structure 1, structure 2, and structure H. These structures are composed of water cavities, which are represented here. So let's first begin by molecules, for example, CO2. And when CO2 enter in contact with water molecules under certain conditions, they form cages. These water molecules form cages, and the gas molecule, the CO2 here, is captured inside the cavity. And the cavity are arranged periodically and form a periodic network of a crystal that form these kind of structures. And not only CO2 can be captured inside these cavities, but also different molecules like nitrogen, carbon monoxide, methane, ethane, propane, and so on. So in this sense, these clathrates are crystalline compounds. So I summarize here some useful properties for the hydrate-based separation process. For 1 cubic meter of gas hydrates contain approximately 172 cubic meter of gas at 20 degrees C and 1 bar, and about 0.8 cubic meter of water. And this is really an interesting property of the performance of the hydrate technique. I summarize also some volumetric properties of gas hydrate, because depending on the structure you form, you can see here that the volume of gas per volume of hydrate is changing. So, and the maximum weight fraction of CO2 can reach 30% for structure 2, for example. And in terms of normalized capacity of structure, we can see that structure 1 can accommodate more CO2 per gram of water than the other structure. I didn't introduce yet the semi-clathrate structure A and B, and these clathrates are alternative structure to these ones because they contain salt molecules in their network. And we can see that these semi-clathrates contain less volume of gas per volume of hydrates, but they have nevertheless interesting properties in comparison to the usual clathrate structure. So because gas hydrate represent a promising method for storing a huge amount of gases, new applications are being developed over the past 10 to 15 years. As we can see here, gas hydrates can be used for cold energy storage, also hydrogen storage, gas transport, but also recently water desalination combined with CO2 sequestration. I can say a word after that. And also in geophysics, where natural gases are of importance either for the recovery or also to destabilize the slope and release methane in the atmosphere. So if you want to know more about this application, you can have a look at the website here of GDR, Groupement de Recherche Hydrate de Gaz, where all these applications are being currently investigated in the French community working on hydrates. A word also about laboratory curiosity. This concerns the anti-clathrate structure, which has been recently discovered, and this may open the way to new application and the development of new gas storage efficiency in this structure. So how does the hydrate-based separation process work? This is here the principle. We have industrial typical flue gas mixtures containing CO2 and nitrogen. The composition is about 3 to 35 percent CO2 in post-combustion. So these molecules are emitted and sent to the capture unit, where the CO2 is then trapped in the hydrate cavities selectively, and only nitrogen, or almost pure nitrogen gas, is then emitted into the atmosphere. And by using pressure variation in the capture unit, the hydrate can be dissociated, and the CO2 can be further reused or stored for reuse for applications, or stored for long-term storage. And the water can be utilized again for another cycle. So this hydrate-based separation process has been patented for CO2 capture by Twain Spencer already 20 years ago, more than 20 years ago. So we can see here a typical conceptual design of a process. This is, for example, in post-combustion. So the flue gas is firstly pressurized using this gas compressor and cooled to the environmental temperature. And this high pressure gas is sent to the hydrate reactor, where it is cooled down to the hydrate formation conditions. And when the equilibrium, vapor liquid hydrate equilibrium is reached, then the main composition of the vapor phase is only the remaining gas. It means it can be nitrogen or hydrogen, which are directly released into the atmosphere. And so the hydrate, which is CO2 rich, is then pumped. This is a hydrate slurry, actually, which is pumped here to a slurry heater and sent to the separator for decomposition, either by heating or by applying a lower pressure to obtain a gaseous CO2 and liquid water. So gaseous CO2 is generally at high pressure, and the liquid water is sent back to the hydrate reactor and cooled down for use in a new cycle. So this typical scheme can be applied either in post-combustion or in pre-combustion. So the formation conditions of the hydrate is divided actually into 3 steps. As we can see on this plot, this is represented here as a function of time. And what we can see is that step O to A is the dissolution of a gas in the hydrate forming gas in the liquid, and step A to B correspond to the nucleation step, where small crystals are forming in the liquid. And finally, from B to C, this is the growth step, where there is a linear increase of gas consumption during this last event. So the hydrate-based separation process is quantified by performance parameters. And this depends on the induction time, on the gas consumption, and also on the recovery and separation factor. So the recovery fraction and separation factor are 2 important parameters. They represent here the quantity that the hydrate can capture, and the selectivity or separation factor represents how good you can separate CO2 from the other gases. So the development of promoters are important to reduce the conditions of formation of the hydrate. And this has been done by adding tetrabutyl ammonium bromide on the system. We can see the effect. This is a thermodynamic effect. This is the equilibrium line of CO2 and water here, what we can see. And this is the stability space where the hydrate can be stable. And when you add this molecule in the system, in the liquid system, to form the hydrate. You can see that this line is shifted to the right, and like this, the formation conditions are reduced. You can form hydrate at already 10 bar and about 9 degrees C. So this is how the structure of a new hydrate look like. This is called a semi-clathrate, and this is where the gas molecule can be captured, the CO2 can be captured and separated from the other molecules. So the selectivity is also important to be evaluated with this new system. But already 20 years ago, Kang and Seo have evaluated the selectivity in water and CO2 nitrogen system, and they show that they can reach about 95% already by a two-stage separation process, and the maximum CO2 to be captured is 8,000 tons per day. And a more recent evaluation using promoters like TBAB have shown that a two-stage process is possible, and with a recovery of 90% of CO2. And like this, the energy consumption compares favorably in hydrate-based separation process to the amine-based, as you can see here, from 1 to 2 kilowatt per kilogram CO2, and in the amine-based it was 2 to 2.8 kilowatt per kilogram of CO2. So let's have a look now at the setup we have developed in Lille. It consists of laser Raman spectroscopy applied to the characterization of gas hydrates. We can see here the reactor where the hydrates are formed. This is the optical reactor where the laser goes through this optical window, and we can probe here either the gas phase or the liquid or hydrate phase in the reactor directly by laser scanning. And we can see here that we obtain a very nice signal of a CO2 in the gas phase, or then we probe the liquid phase here. Then we obtain the signal of the hydrate, which can be discriminated and separated from the contribution of CO2 in the gas phase. So like this, we can recover information on the composition of the hydrate in blue and the composition of gas phase in red. So next we summarize here 10 years of experimental data and experimental efforts to better assess the CO2 capture efficiency in hydrate-based separation process. And so we do cross-laboratory and cross-patch measurements comparison of literature data here in black and our data here in red obtained using our laser technique, our newly developed laser technique. So you can see that first of all there is the literature data are rather scattered in this region. So this is here the gas phase concentration of CO2, and here this is the measured hydrate phase concentration of CO2. And what is important to notice is that all the literature data so far published were obtained using indirect approach. That means that this is obtained by gas sampling and liquid sampling and generally mass balance calculation. So we have now the dotted lines here that correspond to a physical model of the van der Waals-Sampatiu theory of hydrate crystallization, and we see that there is a real good agreement of our data with this theoretical model. So our successful experiment has helped us actually to derive the performance parameters that are coming in the next two slides. So we can see here the performance parameter. This is the selectivity as a function of different parameters, the concentration of CO2. And we were able to show that the selectivity of structure 1 hydrate is better than the one of structure 2, and also that there is a maximum at 20% CO2, which is rather interesting because it corresponds to a typical flue gas treatment, and also that there is some slight but significant influence of pressure and temperature on the selectivity of the hydrate formation conditions. So we have summarized here the meaning of all these measurements. If you have a flue gas inlet of composition of 10%, then the selectivity we obtain of 7-8 means that the composition of the hydrate can be 5 times more important than in the gas phase. And we also derive the recovery. It means that we can capture about 55% of the CO2 in the one stage of hydrate formation. We investigate also the selectivity in semi-clathrate hydrates, which means when adding a promoter to reduce the formation conditions. And we see here, which is summarized here, and we see that for the same inlet composition, we obtain a better selectivity. As we can see here, the hydrate CO2 hydrate compositions can be 8 to 13 times better than in the gas phase. However, the recovery fractions, the capture quantity of CO2 reach 35% in one stage of this, and these results can be have been compared to other group, which depending on the protocol they used, they obtain an even higher selectivity in their semi-clathrate samples. So I want to highlight now some new directions and achievements since 2014. It should be first noted that most of the reported data on HBSP process were obtained in batch mode or semi-batch, which means that they were obtained using a closed reactor in laboratory or gas flowing through water in a reactor. However, to get closer to practical considerations in industrial applications, it is important to develop an experimental proof of a concept I showed you a few slides before. This is what has been done by Sun and co-workers here. This is this diagram. They have developed a new apparatus that allows the continuous formation in this reactor and dissociation in the second reactor of the hydrate for separation of gases. And they showed in several experiments that it is possible to recover more than 65% of CO2 in the hydrate phase, and they use a promoter and they work at atmospheric pressure. So this first preliminary study laid the foundation for potential industrial applications of hydrate separation methods. And I would like also to mention that new chemical promoters and materials or hybrid systems with amines and hydrates are continuously investigated to improve the efficiency of the HBSP process. A second point concerns a new concept that is emerging in the hydrate community. It is based on the decarbonization and desalination at the same time. So how it works, this is a simple block flow diagram of a concept of hydrate-based seawater desalination. So the flue gas containing CO2 is introduced into a reactor, which first contains seawater. At a certain temperature and pressure conditions, seawater or a salt solution could form clathrates or gas hydrates. And during the hydrate formation, the ions and the salts are excluded from the hydrate crystals, and so you obtain pure CO2 and water hydrates that can be then separated, washed and separated, and after dissociating, CO2 is then stored and captured, is then separated for storage, and the water is then water from the dissociated hydrates is pure water and can be used for as potable water. In the remaining salty solution can be separated from the seawater as brine. So this concept of CO2 capture by hydrate-based process and simultaneous seawater desalination is being intensively investigated at present time in the hydrate community, and it's for its potential application in an industrial concept. For the upscaling of the hydrate-based separation process, it is necessary to do a comparative assessment of the efficiency of a process. And first of all, this can be done when considering the CO2 capacity and the storage capacity of CO2 in different process. And we can see that the CO2 capacity for structure 1 or even structure 2 is higher than the maximum capacities achievable for conventional solvents like Selexol, Rectisol, Pro-solvent or Purisol. These solvents are used for physical adsorption in the industry for CO2 separation, but they generally require low temperature in the range of 200K to work, and so they have a negative impact on the economic evaluation. And because the CO2 uptake capacity in hydrate-based separation can be free. So now to summarize and give future directions. So lab scale experimentation showed that the hydrate-based separation process is a novel technology with high potential for CO2 capture. Both chemical, that means promoters, porous materials, and mechanical design of reactors approaches needs to be combined to achieve the ultimate performance of this technology. And more economic and energetic evaluation can lead to a comprehensive comparison of the hydrate-based process with other existing CO2 capture technologies, and this will be presented in the next presentation. And a scaling up of a process will help achieve such assessment and is necessary to develop continuous and semi-continuous setups with proper reactor type and design. So I thank you for your attention and wait for your question. Thank you.
Great, excellent. Thank you, Bertrand, for this very insightful presentation of quite an, I think for many people, very new application of what I understood, one of nature's own long-lived methods for capturing and storing certain compounds. We have 5 minutes left for questions. So once again, I would very much like to open the floor for questions through the same method as we did earlier. Please raise your hand if you have a question to be posed to Bertrand. Michiel Mackey, would you please turn on camera and mic and ask your question?
Thank you for a nice presentation. I was wondering, in your slide, I missed a bit the kinetics. How fast is the process?
Oh, this is an excellent question, because this is we can say one of a difficulty in the hydrate-based separation process. The kinetics can be improved if you add promoters, and generally the people are starting to look at solutions where you mix thermodynamic and kinetic promoters in order to improve the kinetics. One of the big questions is because when you form the hydrate, you sometimes have a layer of hydrate that may hinder the diffusion of a gas to the unreacted water. And so there is some new solutions with porous materials that will improve the process of the kinetic of the process and allows the hydrate system to be efficient kinetically. Yes.
But how fast is the process in comparison to the CO2 absorption in methanol?
Well, for example,
that's very fast.
You can form in 1 minute. You can form hydrates, but it can take also hours if you don't have the good promoter of the good porous material. For example, TBAB, this has been measured in 5 minutes. You already have transformed a lot of hydrates with TBAB or semi-clathrates. It has been measured already in some. I could tell you this paper from, for example, Xiao and Li that have shown in few minutes the formation of hydrates. Yes.
May I ask another question?
Yes.
Okay.
As chairman.
Quick one.
Here you go. Does impurities in CO2 affect your process, like H2S, SO2, NOx, ammonia? That could be also there.
Yes. So
especially on the capacity and also on the rate.
So the impurity is actually very good for hydrates because generally they improve the thermodynamic conditions. There was a study that have shown that SO2 and NOx, they were trapped in the hydrates and they help the system to form the hydrates. So they are good promoter for hydrate formation. So it's not a problem with impurities.
Thank you.
Thank you.
Thank you, Michiel, for your questions. I see another one from Johan Seeman. I hope I pronounced the name correctly, but otherwise you can correct me. Please turn on your camera and mic, if possible.
Sorry, I don't have a camera, but can you hear me?
Yes, we can.
Okay, thanks very much. It's very interesting for me also for the first time to know that CO2 can be stored in a hydrate form. I just want to ask whether the formed CO2-rich hydrate is stable at ambient conditions like normal temperature, normal pressure, or you have to store it in harsh conditions like a high temperature, low temperature.
So in principle, yes, it's an excellent question. In principle, hydrates are unstable at atmospheric pressure conditions. They dissociate generally. If you use a pure CO2 hydrate, you may use an effect called the self-preservation effect, but it's difficult and specific and work in specific conditions. However, as I show in the paper from Sun, they have used a promoter, which is it was THF, and they were able to form the hydrates at atmospheric pressure. So it's really depend on the good promoter you have used and the capture of the CO2 then can be really at soft conditions in this sense. I hope it answers your question.
Yes, thank you.
Okay, thank you very much. I'm very sure I'm just a messenger, but time unfortunately doesn't allow us to address more questions. I see 2 more in the chat. We will make sure we get back to them offline. Well, once again, Bertrand, thank you very much. As I understood, you've had a lot of interest with your research work and your presentation. So once again, thank you very much.
Thank you.
And then I would like to go to our final presentation, which will be given by Jur de Bruin and Mike Essink, who are two master students chemical engineering at Twente University in the Netherlands, and they will tell us about their results of their first explorations on a CO2 capture process, plant design using clathrates. They haven't done this by the two of them alone, but they were part of a team, but they will tell us all about it in the next 25 minutes. Mike, if you would like to take over from here.
Yes, thank you. I will just quickly wait before the presentation is loading. Takes a bit. Yes.
I see it on screen, so I hope everybody does.
Nice. So welcome everybody to the last presentation of this webinar. First of all, I would like to thank the previous speakers for their interesting presentations, and all of you, the guests, for your interest in this topic. In this presentation, we will explore how a plant design would look like using clathrates. But first, before that, I will quickly introduce you to my colleagues to have a face on who are presenting now and who worked on it. Jur de Bruin, who will be a speaker in the second half of this presentation, and Sahil and Joey will join us in the discussion. And the one that you currently hear and probably see speaking is me, Mike. It should be noted that this is a project part of a course, and it's still ongoing. Nevertheless, we have quite some interesting insights to show you. So what can be expected in this presentation? First, we will discuss the goal of the project, followed by a selection of literature that we use to form a conceptual design. And in the conceptual design, we will dive in a bit deeper in the crystallization and the dissociation units, together with the equipment needed for that, and a conclusion and a recommendation on how to proceed further. So the goal is to evaluate if clathrates can be used as an alternative to, for example, the energy-intensive amine process, and the plant design will follow the next principles. We have the blast furnace gas, and we use clathrates to capture the CO2, which we then should process to be able to store it, and the CO is then processed. The design basis that we considered, the feed is of course blast furnace gas of 350,000 cubic meters per hour at a pressure of 1.3 bars and a temperature of 35 degrees, and it contains roughly 25 volume% of CO2. The goal is to have an outlet, for example, for storage. A example project that stores CO2 is the Northern Lights storage, and for this we have to bring it up to spec, and this is at 20 bars and minus 35 degrees, and we should have at least 96 volume% of CO2 in there for this specific project, and other projects are similar to this. So what was our plan of action to explore this technique? First, we did a literature study and considered three clathrate families: the clathrate hydrates, the semi-clathrates, and the hydroquinone-based clathrates. Since most literature was available for the clathrate hydrates, we used this to develop a workflow and a crystallizer model. From this, we got insights on the crystallizer unit itself, and were able to do some calculations on pumps and compressors, and also the release vessel. Thereafter, we used the Hydrate model as the backbone to make a model for the semi-clathrates, more specifically for tetrabutyl ammonium bromide, the TBAP that Bertrand also showed, which again resulted in quite some interesting insights. Then there is the hydroquinone family, which seemed very interesting to us, but we found out that it was too early to explore this type of clathrate, mostly due to lack of data and the fact that it's a gas-solid system. So you have solid particles which are impregnated with the hydroquinone, instead of the gas-liquid solid system like the other two. therefore requiring a completely new model to be developed. Then the literature. This table, I will discuss the pressure and the temperature conditions in the next slide, but most important here is that the pure hydrates have a ratio of water molecules to CO2 molecules that we used of about 6:1. And for the semi-clathlates, this is much higher, of 38:1. We see this back in the formation enthalpies and the dissociation enthalpies, which are much higher for the semi-clathlates. And the adiabatic temperature rise is then higher for the pure hydrates. The growth rate, we already touched a bit upon in the discussion of the last presentation. Here we took the driving force, as a driving force, the partial pressure of CO2 and the a kinetic growth rate constant of 0.49 for the pure hydrates. And here we had to make an assumption, a guesstimation, basically on the basis of literature, that this was around 10 times higher as the one for the pure hydrates. So, as previously mentioned, clathlates need to be stable to be able to exist. And on this slide, we see such diagrams that indicate stability. On the y-axis, we have the CO2 partial pressure. So, and on the x-axis, the temperature. We see for the clathrate hydrates, the red line. Basically, if we're above this line, the clathlates are deemed stable, and below they will dissociate, and the CO2 will be released. For the clathrate hydrate process, we considered a process at 100 bars, so that's 10 megapascals, with a partial pressure of CO2 of 2.5 megapascals, or 25 bars. And then over the column, the CO2 partial pressure will decrease, since we're capturing the CO2 all the way down to the equilibrium line at roughly 14 bars. For the TBAP system, we see that we can go to much milder conditions. Temperature-wise, now we're operating at 11 degrees C instead of 1 degree C. And we can also lower the partial pressure and therefore also the total pressure. So here we consider a process that is at 30 bars with a partial pressure of CO2 of 7.5, and we go all the way back to 0.2. Then the challenges, most literature is still on lab scale and considers mostly binary and sometimes tertiary mixtures. There are no real comparable processes for the crystallizer, since for optimal usage we need a gas liquid solid system, and conventional crystallizers are then you have a pre-saturated liquid which crystallizes, so you get a solid. And it is key for this process to be in contact with the gas at all times. Like we saw in the previous slides, we have quite a high exothermic reaction during this formation. So it is very important to extract that heat because otherwise we might get a temperature increase and then the conditions are not the same anymore. We have limited kinetic data, so we had to make some assumptions, like I explained before, for mostly the semi-clathlates. And now I will explain the conceptual design. So basically, we have to pre-treat the blast furnace gas to get a lot of impurities out, pressurize it, then feed it into the crystallizer, where it then captures the CO2. The hydrates or clathlates are then moved to the CO2 release vessel, where the clathlates are dissociated and the CO2 rich gas is then released. This needs some after treatment and probably repressurization to be able to store it. The CO2 lean gas stream that comes from the crystallizer can then be used for CO processing. In the next slides, we will dive a bit deeper into the crystallizer and explain on how we modeled it, and this resulted in some equipment ideas. And we will do the same for the CO2 release vessel, so where the clathrates dissociate, and we will explain something about the dissociation pressures needed for that, and also some ideas on equipment.
Yes, thank you, Mike. So I will continue with a deeper dive into the crystallization and the dissociation for this process. So first of all, the crystallizer model. So to try and quantify what goes on inside the CO2 capture crystallizer, we created a model. And the goal for this model for us was to be able to determine a few things. First of all, the degree of the clathrate formation, the degree of CO2 removal from the blast furnace gas. Also determine the composition of the gas that is captured by the clathrates, and give also insights into the liquid to gas ratios and the dimensions of the column. Now, to create this crystallizer model, we had to make quite a few assumptions, and here some of the key assumptions are listed. First of all, we assumed constant temperature within the crystallizer. Instead of using fugacity to describe the system, we used pressure, therefore giving us a driving force of the the difference between the partial pressure of CO2 and the partial pressure of CO2 at equilibrium. And for the dissolution of the gas into the liquid, we only considered the liquid side mass transfer resistance. Also, we assumed, as Mike stated before, that for the semi-clathrate, we used a growth rate constant that was 10 times that of the pure hydrate growth rate constant. Yeah. So here is a block scheme to kind of show you a simplified version of how the model works. So at the top are all the components that we consider. In the gas phase, we get a certain partial pressure of the gases, and this partial pressure determines the rate of the dissolution of the gas and the growth of the hydrates. The growth of the hydrates determines the liquid balance and the hydrate balance, and the dissolution of gas determines the liquid balance and the gas balance, and then this gas balance will then determine again the partial pressures of the gases, and that will be one iteration. So what are the main results from this model? So first of all, we looked at what would happen at equilibrium. So we used a very long reactor, and to compare them more effectively, we used for both the pure hydrate and the semi-clathrate the same dissociation pressure in the release vessel and the same extent of crystallization, so the 50 weight% crystals in the liquid slurry. So the main results, what we see is that for semi-clathrates we can produce a lower CO2 content in the CO2 lean stream, and also produce a higher CO2 purity in the CO2 rich stream. And also looking at the kinetics, the gas resonance time is considerably lower for the semi-clathrates, resulting in smaller equipment. However, on the other side, the drawback of the semi-clathrates is that due to a lower capacity, which you see in the mass percentage CO2 in hydrate, we also need a much higher liquid to gas ratio, which means a lot more liquid needs to be handled. Yeah, so here is a kind of, here are the three different balances for the gas, the liquid, and the hydrate for this model. And on the y-axis we see the mole fraction of the gases. So first of all, we see in the gas phase clearly that over the length of the reactor, the content of CO2 goes down, and in the liquid phase you see initially that a lot of CO2 dissolves, and then slowly as the partial pressure decreases, this will also decrease. And in the hydrate we see that we have a CO2 rich composition. Okay, so another important part of this is the release of the CO2 from the hydrates, and especially the influence of the pressure at which we release the gas has an influence on the composition of the gas that we get. And we see that at lower pressures, the composition of CO2 is higher. And as the pressure increases in the release vessel, much more CO2 is dissolved into the liquid again, because it's much more soluble than the other gases. And because of this, the composition decreases. And at a certain release pressure, you will even get that all the CO2 can be stored inside the liquid. Because we assume that in this case, the liquid will probably be saturated after the release. We also looked at this for the different types of clathrates. So first of all, for the pure hydrate at 15% crystallization, we see that there is still quite a large pressure range at which we can effectively release the CO2 because, of course, there is a low liquid content. But on the other hand, we see that for the semi-clathrates, because there is a much larger liquid content, that only at very low pressures is it viable to release this CO2, because otherwise very quickly there is no CO2 left in the gas that is released. And then if we go for semi-clathrates to slightly higher crystallization, so let's say 50%, then we see that because there is again a little less liquid there, that we can again regenerate at slightly higher pressures if we want to. Then kind of give an overview of a process. This is for the semi-clathrates at 50 weight% crystallization and dissociation at 1 bar, to kind of give an overview of the kind of mass flows that are present in this process. So we start off with about 500 tons per hour of blast furnace gas. This then goes to the clathrate formation vessel. Here we show how much liquid we need approximately. We see that we need about 8 kilotons of liquid per hour to capture this gas effectively. This produces CO2 lean gas around 339 tons per hour at 8% CO2 content. And we see that we eventually produce a CO2 rich stream after oxidizing the remaining CO to CO2 of 168 tons per hour at 84% CO2 and 60% nitrogen. At this point, we would then pressurize it and cool it down to be stored. However, at 84% CO2, it's not yet at a high enough concentration to be able to store it. Okay, so then we move on to the energy comparison. And here it's important to note that especially the cooling duty below 20 degrees is important, because this will require expensive refrigerants. And also the electrical duty of the compressors will be an important part. First of all, we see that for the pure hydrates, it actually does not matter a lot if we crystallize to 15% or to 50%. If we then move on to the semi-clathrates, we see first of all, compared to the pure hydrates, a much larger cooling duty required, which makes sense as we have a much larger, first of all, dissociation enthalpy, but also formation enthalpy, but also a much larger liquid stream that needs to be cooled. And for semi-clathrates, on the other hand, we do see that the conditions influence the performance, as we see that at low regeneration pressure, so 1 bar, and high crystallization, so 50%, is clearly the most efficient way to do it. Then we move on to the equipment that we try to design. So here again, like Mike said, we had no reference of real-life applications of such a crystallizer. So in this case, we based ourselves on the results from our model. Especially here, liquid to gas ratios are important, the percentage of crystallization that we want to achieve, and also the transportation of the crystals from the formation vessel to the release vessel are important. In the end, we chose for a co-flow operated bubble column. So at the bottom, gas and liquid are introduced. So the gas bubbles through the liquid, rises upwards, and at the interface it will form these clathrates. And because of the rising velocity of the gas bubbles, the hydrate layer will peel off, and because this hydrate is actually denser than the liquid, the hydrate will sink down to the bottom, and at the bottom we have a conical shape that will collect the clathrates, and we expect to be able to achieve up to 50% crystals here. And because of the pressure difference between the formation and the release vessel, we expect that the clathrate, even at this high solid content, will be able to be pumped to the vessel, as we have 29 bars of difference. But in the case that we do see plugging, we would suggest to use a screw type conveyor to move the crystals to the release vessel.
So then the conclusion and recommendation. First, I will quickly summarize the different processes and compare the two clathrate cases to the amine process, the MEA process. For both clathrate processes, the cooling with refrigerant is significant since we're below 20 degrees C. The good thing is that for the dissociation, we can use rest heat coming from the plant or the cooling for the compressors. We see that the TBAP process requires a very large recycle of solution, which consists of roughly 30% of TBAP and the rest water. We operate at high pressures for both the hydrate process and the TBAP process. However, using the semi-clathrates, the TBAP process, we can reduce it to 30 bars instead of over 100 bars. Unfortunately, both the clathrate processes do not reach the desired outlet concentration with one single stage. So probably, or we have to get a more selective process, or we have to incorporate multiple stages. For the rest, it should be noted that the pressurization of the blast furnace gas before entering the reactor is not fully thrown away, let's say, compared to the MEA process, since often the lean stream that is coming from the reactor or from the MEA process itself has to be repressurized to be able to move it, but also to be able to process it. So that 30 bars or 100 bars is not completely lost and dedicated to this process, since you otherwise had to repressurize it anyhow. For the MEA process, of course, since you have a pure CO2 stream or a smaller stream, this will be lower, the volume, but it's still not fully thrown away. So then the conclusions for the hydrate process, it's still slow, but which results in large column dimensions, like I shown on the last page. The contacting time is 1300 seconds about this for the hydrate process, and for the TBAP process, this is around 100. This is, of course, based on some assumptions we made. We have to operate at high pressures for the hydrate process, and we have a high difficulty to integrate cooling in the crystallizer since we have such large streams, and a lot of heat is released by the formation of the clathrates. Then the semi-clathrates, we need a large amount of refrigerant due to the recycle being that high, since we are cooling below 20 degrees. So then this raises the need for certain refrigerants. There is moderate difficulty to integrate the cooling in the crystallizer. It's still difficult, but a bit less than for the hydrate process, since the amount of liquids which we use is easier to cool than to cool gas. So this integration is still difficult, but a bit less than for the hydrate process. And for now, the processes that we evaluated for the 30% TBAP process and the pure clathrate hydrates are not sufficient to compete with a MEA process, mainly thus because of the cooling costs below 20 degrees, so with refrigerant, and the fact that one single stage is simply not enough to reach the desired specification for storage. So then what will be our recommendation? It would be really nice to have a semi-clathrate salt that is added to be able to operate at higher temperatures so that we can eliminate the need for a refrigerant. So then we have almost the whole process roughly above 20 degrees. That will be very positive for the cooling duties, especially for the refrigerant. Look into a multi-stage crystallization to reach a higher purity of CO2. And do some optimization studies for the pressure, the temperature, and especially the driving force trajectory, and also the weight percent of the additive, for example, the TBAF or the TBAP. It would be nice to have a clear optimum. We chose 30% since that was from literature the optimum, but this was specific for TBAP. Then, of course, since there are only ideas for us now for the equipment and the crystallizer, it should be tested, of course, first on lab scale and then maybe on a pilot plant. If it actually works and if we can reach those contact times, if the heat integration or heat management inside is sufficient. So those are all aspects to look into further. And then maybe also look into the gas-solid system process with hydroquinone impregnated particles. In the industry, we see we can draw an analogy with, for example, catalyst particles. So maybe something like a fixed bed, which should be regenerated once in a while. Those are things we could think of as a recommendation. Then if there are any questions or remarks after the discussion and they're still unanswered, please contact us via these contact information. I think they will also be on the handout. And with that, I would like to open the discussion.
Thank you, Mike and Jur. Very happy with such an excellent presentation as the final presentation of this webinar. Very happy that you were willing to share your insights on these first explorations of such a CO2 capture process design. And it's, as said, first explorations, many open items as you ended with. And I'm very sure that many of the participants are at least as excited as I am, but there will also be questions. I'm pretty sure of that. So as you already mentioned, we have a little bit more than 5 minutes left for 1, 2, or 3 questions. So once again, if somebody has a question, please raise your hand so I can ask you to post a question in this webinar. Who wants to go first? Matthijs Ruitenbeek.
Yeah, thank you, Geoffrey, and thank you all for the presentations. If we link these results of the conceptual process modeling with the actual parameters that we are looking for in the clathrate research, what kind of temperature ranges would make it becoming interesting? Is that orders of magnitude, or is that only a few degrees? How close are we to the desired conditions?
Well, for example, the TBAF, I think we can approximately go 10 degrees higher for the formation. And if we're approximately above the 20 degrees of the formation process, this would eliminate basically the need for refrigerant. And as we saw in, let me see, this slide, that is a very significant part. Which will cost you in the process. So approximately above if we can get above operating conditions of above 20 degrees C.
Okay, thank you.
Oh, I was on mute, Bertrand. I see Bertrand Casalon has a question.
I am just a little bit surprised about the fact that you need more cooling in the TBAB as in the hydrate process. Can you explain more why? I do not catch the thing. Can you understand what I mean?
Yeah, I understand what you mean. Yeah, it's an interesting thing to see initially, but important here to note is, as we've shown before, is that the formation enthalpy is also considerably higher. And another thing to note, of course, is that you need a lot more liquid, and because of this, you require more cooling duty to both because the formation enthalpy is higher and because you have more liquid that you need to cool.
So formation enthalpy will create some heat?
Yes.
So this is this heat that needs to be removed, right?
Yes, in the crystallizer mainly. So that's the E3 block in the middle of this slide. So there heat should be removed to operate at the conditions that we want to. And
also the recycle in the TBAB process considerably higher. So there, also it needs to be cooled with refrigerant. And in the hydrate process, this amount of liquid, it's considerably lower, and thus you require considerably lower amount of cooling duty.
Okay, thank you.
Right, there is still time for one or more questions. I see Federico Consoni, please.
Yes, hello. Thanks for the very interesting presentation. I was thinking, what applications are you foreseeing for the CO processing, and do you think the purity of CO is high enough for being processed in, say, other chemicals application, or would you need some purification process to increase the CO concentration?
As we discussed in this project, we considered storage. We have to say we mainly focused on the process itself and not necessarily on what we could do with the CO2 afterwards. And here we show that, for this single stage, we can get to about 84% CO2. And I don't know about all the applications that would be possible with this gas. But for the storage, they usually want high purity CO2. So in this case, this single stage would not be sufficient for that. But we know that multi-stage process such as that we could achieve high enough purities for these applications.
Sure. And what about the CO, instead the carbon monoxide?
Again, for us that was not the focus of the process. And in the end, here we produce a CO2 rich stream, and the CO2 lean stream contains still a lot of inert in the nitrogen. And I'm not sure about that. Other people could probably say more about that, but you probably desire to remove this N2 before you process the CO.
Yeah, for example, in a Fischer-Tropsch, that would be a lot of room that's taking in a lot of volume, which is inert and cannot be used. So then you handle a lot of dead volume.
Well, it's a nice bridge for me to end the question and answer session and encourage you to register for the event on the 22nd of June in the afternoon from 1 o'clock to 5 o'clock in the afternoon, Central European time. Because there you will also learn that we look at two routes for using the CO, Federico. One goes to ethanol and the other one through fermentation using non-static technology, and the second one is going to naphtha using Fischer-Tropsch. But again, I would strongly encourage you to register for 22nd of June event where we will tell more about that. Okay, then I would like to conclude this webinar, first of all, by thanking our excellent set of speakers. They provided us with a lot of new insights into this interesting, very dynamic and very important domain of CO2 capture. I would like to invite you to join me in a virtual round of applause for the excellent speakers. So I hope they see this and hear this from all of us. Thank you all to you, the participants, for being interested in this topic and for posing your questions. Thanks for that as well. Once again, you will receive from us all the information, all the presentation slides, and we will provide you with a link to the recordings of this webinar. And in the slide on the left-hand side, you see our website, www.carbon2value.be, where you can find more information. You can also find other documentation related to this project. And you will also find a contact form in case you have very urgent questions, remarks, suggestions, or anything else. You can contact us through that contact form on that particular website. That really brings me to the end. Thanks again. And once again, we hope to see you all at the 22nd of June during our end event of this project. Have a nice day. Bye-bye.